Far beyond the stars, the universe appears calm, silent, and complete. But that stillness may be hiding something much deeper. NASA's Roman telescope is designed to scan the cosmos with extraordinary breadth and precision, searching for the invisible forces, hidden structures, and distant worlds that have shaped everything seen today. It may reveal how dark matter bends the universe, how dark energy drives it apart, and how much has remained hidden in the dark all along. If this journey into the unseen universe sounds fascinating, please like the video, subscribe to the channel, and settle in, for NASA's Roman telescope could expose what the universe is hiding. From the widest reachable view, the universe appears as a vast volume of darkness threaded with light. It is not empty in any simple sense. Across the observable universe, galaxies gather in long strands, broad sheets, and crowded junctions, while other regions open into immense gaps where far fewer galaxies shine. This arrangement is often called large-scale structure. It forms over immense spans of time as matter responds to gravity, while space expands. Roman enters this scene not as an observatory concerned first with one object or one small patch, but as one built to look across great areas of sky and gather a broad census of distant light. In that role, it approaches the universe at its widest visible scale, where patterns matter as much as individual sources. The observable universe means the part of the cosmos from which light has had time to reach Earth since cosmic expansion began. Beyond that boundary, if farther regions exist, their light does not arrive here. Within the reachable portion, the sky holds an enormous record of past ages. Farther light comes from earlier times because it spends longer crossing space. A survey that captures distant galaxies across a large area therefore becomes more than a map of positions. It becomes a layered record of cosmic history spread across depth as well as direction. Roman is designed to collect that kind of record with unusual breadth. Its main wide surveys observe invisible and near-infrared light, and infrared means light with wavelengths longer than visible red. This matters because expansion stretches ancient light toward longer wavelengths, making many remote galaxies easier to study in the infrared. On these outermost scales, distance softens familiar detail. A galaxy no longer appears first as a place of stars, gas, and dust. It appears as one point within a population so large that only patterns across millions of such points reveal the deeper structure underneath. Roman's broad survey work is planned to cover more than 5,000 square degrees of sky, about 12% of the full celestial sphere. The value of such width is not simply abundance, it is context. A narrow view can show exquisite detail, but a wide view can reveal how that detail sits inside a far larger design. Roman's wide and deep imaging is expected to record hundreds of millions of galaxies scattered through a large cosmic volume. In this form, the universe stops resembling an isolated collection of bright islands and begins to show its larger geometry. That larger geometry is not laid out like a tidy grid. It looks more like a network shaped by the uneven growth of matter over time. Dense regions draw in more matter and become richer still, while less dense regions lose relative ground as expansion continues. Over billions of years, this process leaves behind a web-like arrangement. Astronomers often describe it as the cosmic web. The phrase is simple, but it points to a real statistical pattern in galaxy distribution. Roman's strength at this scale lies in its ability to survey enough sky and enough distant galaxies to reveal that web in a more complete way. Its purpose is to compare the observed pattern with the one predicted by the best cosmological models, if the two agree closely. the current picture of gravity, matter, and expansion remains strong. If small tensions remain after careful analysis, those tensions may point to missing pieces in the present account. The hidden part of this outer picture is especially important. Ordinary matter, the matter that forms stars, planets, and gas clouds, accounts for only a modest fraction of the total matter content of the universe. Most matter appears to be dark matter, meaning matter known mainly through gravity rather than direct light. Dark energy, in turn, is the name given to the unknown cause of the universe's accelerating expansion. Roman's widest surveys are designed in part to study both of these elusive components by measuring how galaxies are distributed across space and time and how their light is subtly affected as it travels. At the broadest level, this means Roman uses visible galaxies as markers placed throughout the cosmic landscape. Those markers do not reveal the hidden structure by themselves, but in enormous numbers they trace the regions where matter has gathered and the regions where it has thinned away. This is one reason Roman is often described as exposing what the universe is hiding. The phrase does not mean that dark matter or dark energy suddenly become visible in a direct human sense. Rather, it means the hidden influences shaping the universe become more measurable when enough light from enough distant galaxies is gathered with enough uniformity over enough sky. Roman surveys are built for this statistical clarity. The observatory can combine sharp imaging with wide coverage in a way that allows astronomers to examine the shapes, sizes, and distribution of distant galaxies across an immense field. In practical terms, the sky becomes a measured surface rather than a collection of separate pictures. Subtle signatures that vanish in small samples can emerge when millions upon millions of sources are studied together. There is another feature of the outer universe that becomes clearer in such a survey. The bright filaments and clusters of galaxies are only part of the structure. Between them lie cosmic voids, enormous regions where galaxies are much rarer. These voids can span tens to hundreds of millions of light years. They are not completely empty, but they are deeply underfilled compared with the surrounding web. In the largest view, they give the universe a bubble-like appearance, with galaxies marking denser walls and intersections between vast sparse regions. Roman is expected to identify thousands, and likely tens of thousands, of such voids through its large sky surveys. That matters because voids respond in useful ways to the balance between gravity and cosmic expansion. Their shapes, sizes, and distribution provide another route toward testing the broader model of the universe. So the first region in Roman's story is not a place with a surface or an edge that can be touched. It is the grand outer volume of the observable cosmos, as seen through the positions of distant galaxies and the broad arrangement they form. In this region, the individual object matters less than the pattern made by multitudes. Roman's role at this scale is to widen the human record of that pattern, to bring more of the reachable universe into one coherent view, and to make the largest hidden influences easier to measure through the collection of faint, ancient light. After the largest visible pattern comes a slower question about what that pattern is doing over time. The universe does not remain fixed while galaxies simply move through a static stage. Space itself expands, and because of that expansion, the distance between widely separated galaxies tends to increase. This is not a local blowing outward from one central point in ordinary space. It is a general stretching of space on the larger scales. Roman studies this broad change by observing immense populations of galaxies and stellar explosions across long spans of cosmic history. In this region of the subject, the universe is understood not mainly as a web of matter, but as a history of changing scale. Light carries the record of that change. As space expands while light travels, the light is stretched to longer wavelengths. This effect is called redshift because visible light shifts toward the red end of the spectrum, and light beyond visible red moves into the infrared. The greater the redshift, the more the universe has expanded during the light's journey, and in general, the farther back in time astronomers are looking. Roman is built to work strongly in near-infrared wavelengths, which makes it well suited for measuring remote galaxies whose light has been stretched over billions of years. In this way, Roman does not simply look far away, it looks into earlier stages of the expanding universe. The broad aim is to learn how quickly expansion changes across time. In the early universe, matter strongly slows expansion through gravity. Later, as the universe thins out, another influence becomes important. Observations over the past several decades indicate that cosmic expansion is now accelerating rather than merely continuing. The name dark energy is used for the unknown cause of that acceleration. The phrase is a label for an observed effect, not a full explanation. Roman studies the imprint of accelerated expansion on the distances and arrangement of luminous objects. One way to do this is through galaxy clustering, which means the statistical pattern by which galaxies gather and separate across enormous volumes. That pattern contains a faint preferred scale set by sound waves that move through the hot plasma of the young universe before atoms fully formed. Those ancient waves left behind a subtle spacing signal in the later distribution of matter. The signal is often called baryon acoustic oscillation, though the term is only a compact name for an old ripple scale preserved in cosmic structure. Because the physical size of that scale can be inferred, astronomers can use its apparent size at different times to trace how cosmic expansion unfolds. Roman's large redshift surveys are designed to map huge numbers of galaxies precisely enough to follow this standard scale across a wide range of epochs. To do that, Roman needs more than images alone. It also needs a way to sort distant galaxies by time and distance. Part of that work comes from spectroscopy, which spreads light into its component wavelengths so astronomers can identify shifted features and estimate redshift. Part also comes from carefully calibrated imaging across multiple bands. When many galaxies are placed at their approximate distances, a three-dimensional map begins to emerge. The map is not exact in the way a local street map is exact, but on cosmic scales it becomes a powerful measurement tool. It allows astronomers to ask how structures of a given scale appear at different ages of the universe. Roman also studies expansion through a different class of beacon. Some stellar explosions, especially Type 1 supernovae, can be used as distance indicators because their intrinsic brightness can be standardized through careful analysis. A supernova is the explosive death of a star or the explosive disruption of a stellar remnant, depending on the type. Type 1. A events are especially valuable because they have long served as one of the key tools for measuring cosmic distance. Their observed brightness, compared with the brightness expected after calibration, indicates how far away they are. Their redshift shows how much the universe has expanded while their light travels. When both pieces are combined across many epochs, they trace the expansion history in a direct and elegant way. Roman's time domain observations are expected to find an enormous sample of such cosmic explosions. In time domain astronomy, the same regions of sky are observed again and again so that change over days, weeks, months, and years can be measured. This is essential for supernova science because these events brighten and fade over time. Roman surveys are planned to revisit deep fields repeatedly, building light curves, which means records of how brightness changes with time. With many thousands of well-measured Type I supernovae extending to great distances, astronomers can compare nearby and remote expansion more precisely. The result is not a single dramatic image, but a denser timeline of how the universe changes scale. This region remains one of careful uncertainty. Observations already support the broad picture of accelerated expansion, yet the physical nature of dark energy remains unknown. It may be consistent with a constant energy density of empty space, as in the simplest current model, or it may behave in a more complex way. Roman is not expected to solve that question by itself in one decisive stroke. Instead, it sharpens the measurements that any explanation must match. It helps determine whether the simplest model remains sufficient, or whether small departures begin to stand out when data become wider, deeper, and more uniform. So this second region stays with the universe's expanding history. The galaxies spread across Roman's wide fields serve here not mainly as markers of structure, but as clocks and distance points embedded in deep time. Supernovae flash and fade as timed signals from remote ages. Ancient ripples survive as a standard spacing written faintly across the distribution of galaxies. Roman gathers these records across immense reaches of sky and across billions of years of look-back time. In doing so, it studies not only where the universe is, but how its scale changes from age to age, and whether the hidden cause of acceleration follows the simplest path now imagined for it. At the next layer inward, the broad pattern of the universe is no longer read only from where galaxies sit. It is also read from how their light arrives after crossing immense reaches of space filled with matter. Light does not travel through the universe as though gravity were absent. Mass changes the geometry around it, and light follows the changed geometry. When the effect is strong, background objects can appear stretched into arcs or multiplied into separate images. But much of the time the effect is gentler. A distant galaxy appears only slightly altered, its shape nudged by matter lying along the path between that galaxy and the observer. This subtle effect is called weak gravitational lensing, and Roman is built to measure it across wide areas of sky with exceptional precision. A lens in ordinary life bends light because the light moves through glass or another transparent material. Gravitational lensing bends light for a different reason. Matter changes space-time, and the light follows the curved route available within that geometry. The term weak does not mean unimportant. It means the distortion is small, usually so small that no single galaxy image can reveal it with certainty. Galaxies are born with many true shapes and orientations, so one stretched-looking galaxy does not prove that gravity bent its light on the way to Earth. The signal emerges statistically if millions of galaxies across a large field show tiny, coherent alignments. Then a hidden pattern of mass has likely guided their light in similar ways. This is where Roman's design matters greatly. Weak lensing requires both width and sharpness. It needs width because the distortions must be measured across enormous numbers of galaxies spread over very large sky areas. It needs sharpness because the change in a galaxy's apparent shape can be extremely small. Roman combines a wide field of view with image quality that approaches what smaller deep fields have already shown from space. This combination is especially powerful for weak lensing surveys. It allows astronomers to estimate the true distribution of faint galaxy shapes more reliably, and then isolate the slight statistical shift caused by intervening mass. The most important feature of weak lensing is that it traces total mass, not just luminous matter. Stars shine, gas can glow or absorb light, dust can dim and redden what lies beyond it. Dark matter does none of these things in any ordinary observable way, yet its gravity still bends light. Because of that, lensing provides one of the cleanest methods for studying matter that cannot be seen directly. Roman does not photograph dark matter as an object with a surface or colour. Instead, it infers the distribution of mass by studying the patterned distortions imposed on distant background galaxies. In that sense, the unseen landscape begins to emerge through its effect on light from farther realms. There is a deep calmness to this method. The signal is not a bright event or a sudden discovery in a single frame. It appears through patience, calibration, and repetition. Astronomers must measure the shapes of galaxies with great care, understand how the telescope itself may slightly influence those shapes, and correct for other effects such as detector response and image blur. The value of a space telescope is especially clear here because observations from above Earth's atmosphere avoid the shifting turbulence that disturbs fine image detail on the ground. Roman's stable environment and wide survey power are intended to make these measurements more uniform across a vast sample. Weak lensing also carries information about time. Light from very remote galaxies has crossed more of the universe and more of its past than light from nearer galaxies. If the galaxies in a survey can be sorted into rough distance layers, then lensing can be studied in depth as well as across the sky. This approach allows astronomers to ask how the mass distribution changes through cosmic history. The pattern of distortion reflects both the geometry of the universe and the way structure grows under gravity. If dark energy influences expansion, then it also influences how matter has time to gather. Roman therefore uses weak lensing not only to sketch where hidden mass lies, but also to test how the growth of structure unfolds over billions of years. The measured effect is often called cosmic shear. Shear means a slight stretching or skewing of shape. The word cosmic signals that the effect is caused not by one isolated object alone, but by the accumulated matter distribution across broad regions of the universe. Roman's wide surveys are expected to deliver an extraordinary catalogue of galaxy shapes for this work. With so many galaxies measured, the random original directions of those galaxies begin to average away, leaving behind the faint alignment caused by intervening mass. In practice, the universe reveals its hidden scaffolding through an almost whispering influence on the appearance of distant light. There is also discipline in what weak lensing cannot do on its own. The method is powerful, but it demands careful modelling and combination with other measurements. The lensing signal depends on distance, on the large-scale arrangement of matter, and on the underlying cosmological model. It must be interpreted with attention to uncertainty. Observations indicate that weak lensing is one of the best tools available for tracing dark matter and testing cosmic growth, but it remains part of a larger framework of evidence rather than a solitary final proof of every detail. Roman strengthens that framework by making the data broader, deeper, and more internally consistent. In this third region, the universe is no longer simply a pattern of bright sources spread across distance, nor only a history of changing scale. It becomes a medium through which light carries the imprint of hidden mass. Distant galaxies send out their light, and along the way that light is gently guided by matter that shines and matter that does not. Roman studies those faint guided changes with the patience of large numbers and stable vision. Through weak lensing, the observatory turns tiny distortions into a map of the otherwise unseen, allowing the structure of the universe to be read not only in where galaxies are, but in the delicate ways their light has been bent before arriving from the far dark. Within the broad web of cosmic structure, Some regions gather matter far more densely than the long filaments and wide, sparse spaces around them. These are galaxy clusters, the largest gravitationally bound systems in the universe. A cluster is not simply a crowded patch of sky. It is a deep well of gravity, built over immense time as matter flows inward from surrounding structure. Roman reaches this next region by moving from the general pattern of the cosmic web toward its richest knots, where the growth of structure becomes concentrated and easier to measure in bulk. A galaxy cluster contains many galaxies, often hundreds or even thousands, together with vast reservoirs of very hot gas and a much larger amount of dark matter. The galaxies are the visible members, scattered like points across the cluster. The hot gas fills much of the space between them and glows strongly in X-rays, though Roman itself is not an X-ray observatory. Dark matter provides most of the mass and shapes the cluster's deep gravitational framework. When astronomers study clusters, they are not looking only at the galaxies they can see. They are studying the outcome of cosmic growth where visible matter and hidden matter have collected together on immense scales. Clusters matter because their abundance is sensitive to the universe's history. If gravity gathers matter efficiently, then more large clusters form over time. If cosmic expansion, especially accelerated expansion, reduces the rate at which matter can collapse together, then the growth of the largest systems is held back. In this way, clusters are records of the balance between attraction and expansion. They do not announce that balance in a simple statement. Instead, their number, mass distribution, and change through time provide a measured response to the underlying cosmological conditions. Roman's wide surveys help build the large uniform samples needed for this kind of work. The usefulness of clusters begins with scale. A single galaxy can grow in many ways affected by local conditions, internal feedback, star formation, and mergers with smaller neighbors. A cluster is also complex, but because it forms from such a large region, its overall abundance becomes a cleaner tracer of cosmology. The universe either produces a certain number of very massive clusters by a given time, or it does not. That makes clusters especially valuable in statistical studies. Roman is designed to observe large areas of sky deeply enough to identify clusters over broad ranges of distance. Some will be seen relatively nearby in cosmic terms. Others will be seen much farther away, from earlier eras when the universe was younger and the larger structures were less mature. Finding clusters in survey data can happen in several ways. One route is to identify concentrations of galaxies that lie at similar distances, forming an overdense region against the background sky. Another route is to detect the way a cluster's mass bends the light of still more distant galaxies behind it. Roman's sharp, wide-field imaging contributes to both approaches. It can help locate dense galaxy populations, and it can help measure the weak gravitational lensing signal that reveals how mass is distributed in and around clusters. In this way, Roman helps connect what is seen directly with what is inferred through gravity. The growth of clusters is not sudden. It is a long process in which smaller groups and filaments feed larger structures. Matter falls inward, galaxies interact, smaller groups merge, and the central gravitational well deepens. Some clusters are relaxed, meaning their contents have had time to settle into a more regular arrangement. Others are disturbed, carrying signs of recent mergers and continued assembly, across large samples. This diversity becomes part of the story of structure growth. Roman surveys are valuable because they do not isolate only a few famous examples. They create the possibility of studying many clusters across time in a consistent framework, allowing the universe's general habits to become clearer than the peculiarities of any one system. Clusters also help clarify the role of dark matter. The visible galaxies in a cluster do not supply enough mass to account for the gravitational effects observed. The hot gas adds more mass, but still not enough. Weak lensing and other mass estimates show that a much larger dark component is present. In cluster regions, the hidden and visible parts of the universe lie close together in a form that can be measured from several angles. Roman contributes to this by helping map the lensing signal around clusters and by expanding the number of clusters available for comparative study. The result is not a direct portrait of dark matter itself, but a more detailed picture of where mass must lie in order to produce the observed behavior of light and structure. There is also a quiet importance in emptier regions around clusters. A cluster is never fully separate from its surroundings. Filaments connect it to other dense regions. Matter continues to move through those bridges over time. Roman's wide surveys help preserve this environmental context. A narrow observation might show the crowded core of a cluster beautifully, but the larger cosmic landscape that feeds the cluster can be harder to see. Roman is built to retain that larger setting while still providing fine enough detail for population studies. This makes clusters less like isolated islands and more like major intersections within a living network of matter. In this fourth region, the universe appears as a field of growing gravity gathered into its largest bound concentrations. Galaxy clusters represent the places where cosmic structure becomes especially massive, statistically revealing, and deeply shaped by the contest between gravity and expansion. Roman studies them not to admire their scale alone, but to use their presence, numbers, and mass as evidence of how the universe builds itself over time. The broad web remains in the background, but here its densest knots take center stage as records of growth written in galaxies, hidden mass, and the slow assembly of the largest structures that gravity can hold together. After the great knots of galaxy clusters, the view settles into the galaxies themselves, not as individual worlds to be examined one by one, but as an immense population spread across Roman's wide fields. A galaxy is a vast system of stars, gas, dust, dark matter, and the quiet space between them, held together by gravity and shaped over long spans of time. On the scale Roman surveys, galaxies fill the sky in enormous numbers. Some are near enough to show internal structure clearly. Many more are distant, small, and faint, carrying light from much earlier ages. In this region of the story, Roman becomes a census taker of galaxies across cosmic breadth, building a record of how they appear, how many there are, how they differ, and how their populations change with time. The value of such a census begins with number and uniformity. A few carefully chosen galaxies can teach much about local detail, but they cannot fully reveal the habits of the galaxy population as a whole. Roman is designed to image huge areas of sky with high resolution and high sensitivity in near-infrared light. That combination allows astronomers to gather measurements for hundreds of millions of faint galaxies within a single broad scientific framework. Each galaxy contributes only a little to the full picture, but in aggregate they become a statistical archive of cosmic evolution. Galaxies do not all share one form. Some are broad spirals with graceful arms, dust lanes, and bright regions of ongoing star formation. Some are smoother elliptical systems, where the light appears more evenly spread and active star formation is often much reduced. Others are irregular, disturbed, or caught in the aftermath of interaction. These differences are not merely visual decoration. They reflect how gas cools, how stars form, how mergers reshape structure, and how a galaxy's environment affects its history. Roman's wide survey images will allow astronomers to study shapes, sizes, orientations, and brightness profiles across vast numbers of galaxies rather than only within a few selected samples. Near-infrared light is especially useful for this work. It helps astronomers see galaxies whose light has been stretched by cosmic expansion from shorter wavelengths into longer ones. It also gives a clearer view through moderate amounts of dust, both within distant galaxies and within regions of the Milky Way that lie between Earth and the deeper sky. Because of this, Roman can extend galaxy studies farther back in time while maintaining broad coverage. Distant galaxies that might appear dim or incomplete in a more limited view become part of a wider, more balanced census. The result is a map not only of where galaxies are, but of what kinds of galaxies populate different epochs of the universe. This is important because galaxy evolution is not a single path. Some galaxies grow steadily through long periods of star formation. Others consume or lose their gas and become quieter. Some merge with neighbors and emerge transformed in shape and stellar content. Some remain small and faint, while others become massive systems with dense, central bulges and extended halos. Roman's wide-field surveys help reveal how common these different paths are. They allow astronomers to compare galaxy populations across distance ranges that correspond to different cosmic ages. The farther the survey reaches, the earlier the sample population becomes. In this way, the galaxy census also becomes a historical sequence. Roman's width matters as much as its depth. Galaxy properties are influenced by surroundings. A galaxy in a dense environment may evolve differently from one in a more isolated region. Wide surveys preserve this context. They show whether a galaxy lies near many neighbors, along a filament, in the outskirts of a cluster, or in a quieter field. This environmental information is essential because the life of a galaxy is never entirely separate from the larger structure around it. Gas supply, encounters, stripping, and mergers all depend in part on surroundings. Roman makes it possible to study galaxy form and environment together over an enormous stretch of sky. There is also a practical calmness in Roman's approach. Because the observatory will gather measurements across such large contiguous areas, the resulting data can be compared internally with less dependence on stitching together many very different small surveys. Uniform observing strategy reduces some kinds of selection bias and helps astronomers know whether an apparent trend is likely to be cosmic or simply an artifact of how the data were collected. This is especially important when dealing with faint, distant galaxies, where small observational differences can otherwise produce misleading conclusions about size, brightness, or abundance. The census Roman builds is not confined to the brightest and easiest objects. One of its strengths is that it extends toward the faint population that fills the universe far more abundantly than the rare giant systems that first catch human attention. Small galaxies, modest galaxies, and remote galaxies all matter because the universe is built from populations, not from spectacular exceptions alone. Many of the processes that shape cosmic history become clearest only when common systems are counted carefully. Roman's wide and sensitive view helps recover that fuller demographic picture. In this fifth region, galaxies are treated as the main inhabitants of the broad cosmic landscape. They're no longer just markers for large-scale structure, nor only tools for measuring expansion. They become the subject in their own right, observed across vast numbers and broad distances so that their forms, distributions, and histories can be compared on one coherent scale. Roman's gift here is not simply magnification or closeness. It is breadth joined to clarity. It gathers enough galaxies, over enough sky, across enough time, to let the population speak for itself. Through that population, astronomers can trace how the visible universe of galaxies becomes what it is, not through isolated examples, but through the slow, cumulative record written across millions upon millions of stellar systems. After the broad census of galaxies comes a quieter but more restless layer of the sky, where the same deep fields are not only mapped but watched. A single image can suggest stability. Distant galaxies seem fixed in place, their faint light spread across the dark with no visible motion. Yet when the sky is observed again and again, change begins to emerge. Points brighten, fade, appear, and disappear. Some changes last days, some unfold over months, some mark the deaths of stars, some come from matter falling onto compact objects, some remain rare enough that they are known mainly through patient repeated surveys. In this region, Roman studies the deep universe not as a still landscape, but as a changing one. This kind of work is called time-domain astronomy. The phrase means observing the same regions repeatedly, so that variation with time becomes part of the measurement. Roman is especially well suited to this because it combines a wide field of view with sharp infrared imaging and stable observing conditions in space. A wide field matters because many transients, meaning objects or events that change noticeably over time, are uncommon at any one location on the sky. Sharp and stable imaging matters because astronomers need to compare one observation with the next, and know that apparent differences are caused by the sky itself rather than by shifting atmospheric conditions or unstable instrument behavior. Roman brings both breadth and consistency to this work. In the deep extragalactic sky, one of the most important changing sources is the supernova. A supernova is a stellar explosion bright enough to outshine, for a time, much of the surrounding light of its host galaxy. Though the star that explodes is tiny compared with the whole galaxy, the released energy can make the event visible across immense distances. This makes supernovae powerful markers in the distant universe. Roman's repeated observations of carefully selected fields are expected to detect very large numbers of these events, including many at distances that are difficult to sample well with smaller or narrower surveys. Not all supernovae arise in the same way. Some come from the core collapse of massive stars after nuclear burning can no longer support the star against gravity. Others, especially type 1a supernovae, arise from white dwarf systems under special conditions that lead to thermonuclear disruption. Type 1. A events are especially important in cosmology because their brightness can be standardized through careful calibration. That means they serve as distance indicators across deep time. In this changing sky region, Roman does not treat these explosions only as dramatic events. It treats them as timed beacons whose rise and fading carry measurable information about distance, redshift, and cosmic expansion. To use supernovae well, astronomers need more than a single bright detection. They need a light curve, which is a record of how brightness changes with time. Different kinds of supernovae brighten and fade in different ways. Even within one class, the shape of the light curve helps reveal intrinsic properties and improves distance calibration. Roman's repeated infrared observations allow those curves to be traced with regularity. Because the observatory can return to the same fields over and over, the event is not frozen at one unknown moment. It is followed through part of its life, from early brightening through later decline. In this way, time itself becomes an observed dimension of the survey. Infrared measurements are especially valuable for distant supernovae because the light from remote events is stretched toward longer wavelengths by cosmic expansion. A supernova that emits strongly at visible wavelengths in its own rest frame may be observed partly in the infrared after its light has crossed billions of years of expanding space. Infrared observations can also reduce some of the effects of dust, which can dim and redden light in ways that complicate distance work. Dust is never removed as a problem entirely, but Roman's wavelength range helps astronomers recover cleaner measurements for many distant events than would otherwise be possible. The changing deep sky contains more than supernovae. Some galaxies host active central regions powered by matter falling towards supermassive black holes. These active nuclei can vary in brightness over time. Some stars in distant systems change in regular or irregular ways. Some rare events may appear only briefly and challenge easy classification at first. A broad time domain survey is valuable precisely because it does not limit attention only to the expected. When a large area is watched repeatedly with sensitive instruments, the universe reveals both the populations already known and the outliers that occupy the edges of present understanding. Roman's survey design makes room for both. It can recover large standardized samples for planned cosmological study, while also opening discovery space for uncommon transients. There is a measured discipline in this kind of survey. The scientific gain does not come from one extraordinary image alone. It comes from cadence, comparison, and completeness. Cadence means the rhythm of repeated observations. If the return interval is well chosen, many events can be caught early enough to identify and follow. Comparison means each new image is aligned with earlier ones so that real changes stand out against the persistent background of galaxies and stars. Completeness means understanding what kinds of events the survey is likely to detect well, and which ones may be missed because they are too faint, too brief, or too rare. Roman's strength lies not only in finding changing sources, but in doing so in a systematic way that supports statistical science. This sixth region therefore remains in the distant universe, but it adds motion to what had seemed still. The galaxies mapped in the previous view now become hosts for brief flashes and slow variations. Light no longer serves only as a marker of location and age. It becomes a record of change unfolding across days, months, and longer intervals. Roman's role is to keep watch over broad, deep fields with enough sensitivity and regularity that the hidden activity of the extragalactic sky can be measured rather than merely noticed. In that patient, repeated watching, distant explosions, variable nuclei, and other transient sources rise out of the apparent calm, showing that even the far universe is not static when observed with enough care and enough time. After the great surveys of distant galaxy populations, the view comes inward to a quieter neighborhood of the universe, where galaxies are near enough that their outskirts, companions, and faint traces of past assembly can be studied in greater detail across wide fields. These are not the most remote systems whose light arrives from the earliest accessible ages. They are nearer galaxies, still far beyond the Milky Way in most cases, yet close enough that Roman can treat them not only as compact sources in a vast census, but as extended systems with structure spread across the sky. In this region, Roman studies the nearby galactic neighborhood as a collection of histories written in disks, halos, dwarf companions, and stellar streams. A nearby galaxy is valuable because distance changes what can be measured. In very remote systems, Roman records the broad appearance and statistical properties of whole galaxies. In nearer systems, It can often separate brighter stellar populations, trace subtle changes across a galaxy's extent, and follow faint structures that lie far outside the bright central body. This does not make nearby galaxies more important than distant ones. It makes them a different kind of record. They preserve the outcomes of galaxy growth in a form that can be examined across entire systems, instead of only inferred from integrated light. Roman's wide field is especially useful here because a galaxy is never only its central bright disk or bulge. Its history is often written in the dim outskirts that many narrower observations miss. Those outskirts matter because galaxy formation is cumulative. A galaxy does not appear in finished form and remain unchanged. It grows through star formation, accretion of gas, and interaction with smaller companions. Some of those companions survive as dwarf satellite galaxies. Some are stretched apart by gravity and leave behind streams of stars. Some are absorbed more completely, adding stars and dark matter to the outer halo. Over long spans of time, these events build a layered record around a galaxy, especially in its faint outer regions. Roman is well suited to tracing such records because it can image large surrounding areas with stable, sensitive, near-infrared vision. The outskirts do not blaze brightly. They must be recovered through breadth, uniformity, and careful measurement. A stellar stream is one of the clearest signatures of past interaction. It forms when a smaller system, such as a dwarf galaxy or a globular cluster, is gradually torn apart by the gravity of a larger host. Its stars do not vanish. They spread along elongated paths that preserve something of the orbit and the disruption history. These streams can be very faint, especially in external galaxies, and some are only partly known at present because the required combination of wide field and fine detail is difficult to achieve. Roman offers a path toward much broader discovery of such structures. By imaging large areas around nearby galaxies, it can help reveal the thin and diffuse trails that mark earlier episodes of capture and loss. These streams are sometimes described as galactic fossils. The word fossil here does not mean something dead in a literal biological sense. It means a preserved trace of earlier formation events. A galaxy may look smooth and settled in its inner regions while its outskirts still carry debris from past accretion. Roman's contribution in this region is to widen the search for those preserved traces across many nearby systems rather than only within a few famous examples. That matters because galaxy assembly is not learned best from a single case. It becomes clearer when many galaxies of different masses and environments are examined in similar ways. Dwarf galaxies are another important part of this nearby neighborhood. They are small, faint systems, often rich in dark matter relative to their visible light, and they can orbit larger galaxies as satellites or exist more independently in looser environments. Because they are faint, many likely remain undiscovered or poorly characterized beyond the very nearest groups. Roman's wide and sensitive imaging can expand the accessible sample of such galaxies, especially at low surface brightness, where light is spread thinly across the sky. Low surface brightness means a galaxy may contain many stars in total, yet still appear difficult to detect because its light is not concentrated. In this way, Roman can help recover parts of the nearby galactic population that traditional searches miss or measure only incompletely. Nearby galaxies also allow Roman to study gradients across a single system. A gradient is a gradual change from one region to another in galaxies. Brightness, color, stellar population age, and dust content often shift with distance from the center. Star formation may be more active in some parts of a disk and quieter in others. The outer regions may preserve older or more easily disturbed populations. A wide field makes it possible to measure these changes over the full visible extent of many galaxies, rather than sampling only a narrow central patch. This matters because partial views can give a misleading impression of a galaxy's whole life. Roman's breadth helps restore the full spatial context. There is a further advantage in Roman's ability to resolve individual bright stars in some nearby systems. Even when most stars remain blended into smooth light, the brighter populations can still be counted and mapped. These stars provide clues to age, stellar evolution, and the recent history of star formation in different parts of a galaxy. Observations indicate that Roman's near-infrared imaging can extend this kind of resolved stellar work across wider areas and to greater numbers of nearby galaxies than has previously been practical at similar sharpness. The gain is not simply more pictures, it is a more complete demographic record of stellar populations spread through real galactic structure. In this seventh region, the nearby universe becomes a place where galaxy history is visible in the outskirts as much as in the center. Roman studies neighboring galaxies not only as luminous systems in a census, but as assembled structures surrounded by evidence of growth. Faint streams trace disruption. Dwarf companions reveal the smaller building blocks that still remain. Extended halos and outer disks preserve slow accumulation over time. Through wide and steady infrared surveys, Roman helps turn these surrounding traces into readable evidence, showing how galaxies in the local cosmic neighborhood carry within their full extent the record of how they become what they are. After the nearby galaxies beyond the Milky Way, the view comes inward again to the galaxy that contains the Sun. Seen from within, the Milky Way is not laid out before the eye as a clear spiral design. It surrounds the observer from inside its disk, and much of its structure is hidden behind clouds of dust and immense crowds of stars. In visible light, many directions through the galactic plane appear darkened, reddened, or confused by overlap. The galaxy is present in abundance, yet much of it remains difficult to read. In this region, Roman studies the Milky Way as a dusty panorama, using infrared light to recover parts of the home galaxy that ordinary visible observation cannot show clearly. Dust in space is made of tiny solid particles mixed with gas. The grains are extremely small, yet spread through vast interstellar clouds they have a strong effect on starlight. Shorter wavelengths are scattered and absorbed more readily than longer wavelengths, so visible blue light is hindered strongly while longer infrared light can pass through more easily. The result is that regions which look opaque or deeply dimmed in visible light can become far more transparent in the infrared. Roman takes advantage of this basic property. Its near-infrared vision allows it to peer through much of the dust that veils the Milky Way's disk, revealing stars and structures that would otherwise remain concealed or only partly known. The Milky Way is a barred spiral galaxy, meaning it contains a flattened disk with spiral arms and a central elongated bar-like structure. But from the Sun's position inside the disk, these broad forms are not directly seen in the way an outside observer would see them. Instead, the home galaxy appears as a bright band across the sky, dense in some directions and interrupted in others by dark lanes of dust. Roman's role in this region is not to create a simple artistic portrait of the Milky Way from outside, but to improve the measured map of what lies along many lines of sight within it. The observatory can survey crowded fields efficiently and with sharp resolution, turning a confused layered foreground into a more readable galactic record. Crowding is one of the great practical problems of Milky Way observation. In dense directions, especially toward the galactic plane, stars overlap on the sky in huge numbers. A single patch of sky can contain an extraordinary concentration of sources at different distances with different intrinsic brightness and behind different amounts of dust. A wide field alone is not enough in such regions. Sharp imaging is also needed to separate neighbouring stars and measure them reliably. Roman combines both qualities. It can cover broad areas while resolving far more sources in crowded dusty fields than a blurrier wide survey could manage. In this way, the home galaxy becomes less like a luminous haze and more like an ordered field of individual measured stars. This is important because the Milky Way is not only obscured, it is layered along one line of sight through the disk. Nearby stars, distant stars, star-forming clouds, remnants of older stellar generations, and diffuse interstellar material may all overlap. Dust dims some stars more than others, making the true distribution harder to infer. Infrared surveys help sort out this complexity. When combined with brightness and colour measurements, they allow astronomers to estimate how much dust lies along different paths and to recover more of the underlying stellar population. Roman's wide and sensitive infrared maps therefore help not only by seeing through dust, but by allowing the dust itself to be charted more clearly. The galactic plane is especially rich in this kind of hidden structure. It contains the spiral arm environment, where much of the Milky Way's gas and dust are concentrated. In these regions, new stars are born within cold, dense clouds, while older stars continue their orbits through a medium shaped by previous generations of stellar activity. Visible light observations often reduce such fields to patches of obscuration broken by bright foreground stars. Infrared observation reveals a much fuller scene. Faint embedded populations, reddened distant stars, and the texture of the stellar background all become more accessible. Roman's broad infrared surveys help turn these obscured regions into a more complete map of galactic content. A map of this kind is not purely geographic in the ordinary sense. It is also demographic. Roman can help count stars across different parts of the Milky Way, compare how dense they are in one region versus another, and trace how stellar populations change across dusty environments. It can also help identify rare or unusual sources within the crowd, because the surrounding field is measured with such breadth and consistency. In practice, this means the observatory gives astronomers a more faithful accounting of what the galaxy contains in regions where visible light provides only a partial census. The hidden does not vanish entirely, since some dust clouds are still extremely thick even in the infrared, but much more of the galactic landscape becomes legible. There is a quiet shift in perspective here. In the earlier outer sections, Roman studies galaxies as distant systems, or uses them as traces of the large universe. In the Milky Way, the observatory becomes a surveyor of the environment through which the sun itself moves. The challenge is no longer only distance, but obscuration and density. The light is abundant, yet it is mixed, reddened, and partially blocked. Roman addresses that challenge with wavelength, resolution, and coverage. It sees along the crowded lanes of the galaxy in a way that makes hidden stellar populations more recoverable and the distribution of dust more measurable. In this eighth region, the Milky Way appears as a vast interior landscape veiled by interstellar dust and crowded with overlapping stars. Roman's infrared eye does not remove that complexity, it works through it. By passing more effectively through dusty regions and resolving dense stellar fields across wide areas, the observatory helps transform the home galaxy from a partially obscured band of light into a more detailed panorama of structure and population. The result is a broader, calmer, more complete view of the galaxy from within, where much that seems dark in visible light gives way to a deeper field of stars and interstellar matter. revealed through the longer reach of infrared light. From the broader dusty panorama of the Milky Way, the view narrows toward one of its most crowded inner regions, the galactic bulge. The bulge is the dense central concentration of stars near the heart of the home galaxy. It lies toward the inner Milky Way, behind heavy dust and across a line of sight packed with overlapping stellar populations. In visible light, much of this region is difficult to read clearly. In near-infrared light, however, far more of the hidden population comes through. Roman enters this region not to inspect the galactic center as a single bright object, but to watch selected dense fields within and around the bulge over and over again, turning a crowded inner sky into a record of subtle change. The bulge is valuable because of its abundance. It contains an extraordinary number of stars projected into a relatively small area of sky. Where stars are numerous, rare events become more findable. Roman's bulge survey is built around this basic truth. It observes several carefully chosen fields in the inner galaxy, where the density of stars is high enough that even unlikely temporary brightenings will occur in measurable numbers when enough stars are watched for long enough. The strategy is not based on one extraordinary object. It is based on population, cadence, and persistence. The sky becomes a monitored field of possibilities. One of the key phenomena Roman studies in these fields is gravitational microlensing. Lensing, in general, means the bending of light by gravity. In the weak lensing of distant galaxies, the effect is statistical and spread across vast cosmic structure. In microlensing, the scale is much smaller and the event is temporary. A foreground object, often a star or a faint compact body, passes close enough to the line of sight to a more distant background star that its gravity bends and focuses the background light. The background star then appears to brighten for a time and later return to its earlier level. No new light source is switched on. The geometry of light has briefly changed. The word micro does not mean the effect is tiny in significance. It means the angular scale of the lensing is very small. In most cases, the separate light paths cannot be resolved into distinct visible images by the telescope. What Roman measures instead is the temporary change in brightness. The event has a characteristic rise and fall shaped by the motion of the source, the lens, and the observer. This shape is called a light curve in crowded bulge fields, where millions of stars can be monitored. Many such light curves can be found if the observations are frequent and stable enough. Roman is designed precisely for that kind of repeated watching. The inner Milky Way is the natural place for this survey, because it provides both the dense background of source stars and a large population of possible foreground lenses along nearly the same direction. Stars in the disk can lens stars in the bulge. Stars in the bulge can lens other bulge stars. Faint stellar remnants and low-mass objects can contribute as lenses as well. The result is a rich lensing environment in which gravity reveals itself through time-dependent changes in starlight rather than through a static image. Roman's near-infrared view is essential here because dust would otherwise hide too much of the bulge behind darkened and reddened veils. There's a practical elegance in the survey design. Roman does not simply glance at the bulge and move on. It returns repeatedly with high cadence, meaning short intervals between observations, so that brief changes can be followed from beginning through peak and decline. This is important because a microlensing event is not announced in advance. If observations come too rarely, the moment of strongest brightening may be missed, or the shape of the event may be sampled too poorly to interpret with confidence. Repeated visits at a steady rhythm allow the event to be reconstructed as a physical process rather than merely noticed as an unexplained fluctuation. The chosen bulge fields also reflect the observatory's geometry and orbit. Roman can view this inner galaxy region during repeated observing windows, building multiple seasons of monitoring across the mission. This matters because the bulge is not interesting only in one brief interval. The power of the survey comes from returning to the same fields over extended periods and gathering a deep time record of changing sources. Some microlensing events are short, others unfold over longer durations. Beyond lensing itself, the same survey can capture many classes of variable stars and other transient behavior within the dense stellar environment. The bulge thus becomes not only a target region, but a living laboratory of time-domain astrophysics. Crowding again plays a central role in such dense fields. Many stars lie so close together on the sky that reliable measurement demands sharp imaging and stable calibration. Roman provides both from space. Without atmospheric turbulence, the recorded point spread of each star remains much more controlled, and that helps astronomers separate neighbouring sources and measure subtle brightness changes more accurately. This is crucial because microlensing often reveals itself through smooth, temporary amplification superimposed on an already crowded background. If nearby stars are blended too strongly, the event can be mismeasured or missed. Roman's combination of resolution, sensitivity, and field size makes the inner bulge far more tractable than it would otherwise be. The deeper value of bulge microlensing is that it studies mass through gravity alone. The lens does not need to shine brightly. It only needs to pass close enough to the line of sight that its gravity alters the path of the background starlight. This makes microlensing sensitive to objects that are difficult to detect by ordinary emitted light. In that sense, the bulge survey continues Roman's broader theme of exposing what is hidden, but now on a more local and intimate scale. The hidden is no longer only dark matter shaping the cosmic web. It is also the unseen or faint mass within the crowded inner galaxy, briefly made measurable through the bending of light. In this ninth region, the Milky Way's inner star fields become a domain of monitored gravity. Roman looks toward the bulge through dust in infrared light and watches millions of stars with patient repetition. The crowded background that once seemed like an obstacle becomes the very reason the survey works. Within that crowd, temporary brightenings rise and fade as foreground masses pass across delicate alignments of light. Through these events, the dense inner galaxy reveals itself not merely as a bright central concentration, but as a field where gravity acts visibly in time, turning hidden masses and crowded starlight into a readable pattern of change. Within the repeated microlensing watch of the galactic bulge, another layer of hidden structure begins to appear. The temporary brightening of a background star may at first seem to describe only the foreground mass that passes in front of it. Yet in some events, the smooth rise and fall is interrupted by a smaller and briefer deviation. That extra feature can reveal the presence of a planet associated with the foreground lensing star, or in some cases a planet wandering without a host star at all. In this region, Roman's bulge survey turns from microlensing as a general effect of gravity to microlensing as a method for discovering worlds that are otherwise extremely difficult to find. Most exoplanet searches are naturally most sensitive to planets that pass in front of their stars from Earth's point of view, or to planets that tug their stars strongly enough to create measurable motion. Those methods have transformed planetary astronomy, but they favour certain kinds of systems. They're often strongest for planets close to their stars or for planets whose repeated effects are relatively easy to trace. Microlensing offers a different window. It does not depend on a planet shining with its own light, and it does not require many repeated orbits to make the planet known. It depends on gravity, alignment, and patient observation of an immense number of background stars. When a foreground star acts as a lens, the light curve of a background star normally follows a smooth pattern. If the foreground star carries a planet, the planet's gravity can slightly alter the lensing geometry. This produces a brief anomaly in the light curve, a small departure from the simple rise and fall expected from a single lensing mass. The anomaly may last hours or days rather than the longer span of the main event. Its exact shape depends on the planet's mass, its projected position relative to the host star, and the geometry of the alignment. Roman's role is to measure these deviations with enough precision and enough frequency that they can be recognized and interpreted across a very large statistical sample. This approach is especially powerful for planets that lie at moderate or wide distances from their stars, often beyond the region where other leading search methods are most sensitive. These are colder planetary environments, receiving much less starlight than the close hot worlds that first dominated exoplanet discovery. Roman is therefore expected to expand the planetary census into territory that remains relatively underexplored. It can detect planets whose masses range down toward the scale of Earth, and even lower in some favourable cases, especially when the lensing conditions are well aligned and the measurements are dense and precise. The result is not merely a longer list of planets, it is a more balanced account of planetary systems across a broader range of orbital environments. The importance of cold worlds is not only that they are numerous, they carry information about how planetary systems form and arrange themselves. The outer regions of a planetary system are where giant planets often take shape and where smaller icy bodies can remain. The spacing and mass distribution of planets in these colder zones help test models of how protoplanetary disks evolve and how planets migrate after formation. Roman's microlensing survey does not see these systems in the same way a direct image would see them. It detects their gravitational imprint during chance alignments. Yet when many such detections are combined, the unseen architecture of distant planetary systems begins to emerge statistically. This method is also unusually sensitive to low-mass planets that would otherwise be difficult to detect at large orbital distances. A planet does not need to complete many orbits during the observing campaign. It only needs to disturb the lensing event at the right moment. That makes microlensing a survey of opportunity written in geometry rather than repetition. Roman's wide field and high cadence are crucial because the anomalies can be short and the relevant alignments are rare for any one star. Only by watching millions of stars repeatedly can the survey build a large enough yield. Observations indicate that Roman may discover thousands of planets through microlensing, including many with masses and orbital separations that remain underrepresented in present catalogues. Among the most striking possibilities are free-floating planets. These are planetary mass objects not clearly bound to any star. Some may have formed in relative isolation like very small failed stars, while others may have formed in planetary systems and later been ejected by gravitational interactions. It remains uncertain how many such worlds exist and what fraction arise from each pathway. Microlensing is one of the few methods that can detect them in substantial numbers because a free-floating planet can still act as a lens even if it emits little or no visible light. Its event is typically shorter than the event caused by a star, since the lensing mass is smaller. Roman's cadence and sensitivity make it especially well suited to finding these brief signals. In this way, the survey can probe not only planets in orderly systems, but also planets moving alone through the galaxy. There is a calm exactness to what Roman provides here. The observatory does not examine one nearby planetary system in intimate detail. It does something broader and, in its own way, more revealing. It samples the planetary population of the Milky Way statistically, across thousands of systems distributed through the inner galaxy. Some host stars will be unlike the Sun. Some planets will orbit far from their stars. Some will be smaller than the worlds most easily found before. Some may have no star at all. The survey therefore helps answer not whether one particular kind of planetary system exists, but how common different kinds of systems are across the galaxy. This exoplanet census is shaped by uncertainty, but it is productive uncertainty. Roman is expected to detect planetary signals with a richness not yet available from existing microlensing surveys, yet the exact yields will depend on the true galactic population of planets, the distribution of host stars, and the detailed behavior of the lensing events themselves. Observations and modeling strongly indicate that Roman will provide a major advance in sensitivity to cold and low-mass worlds. What remains open is the full inventory the Milky Way will reveal when such a survey is finally carried through at scale. In this 10th region, the crowded bulge fields become a doorway to hidden planets. The same monitored brightenings that reveal foreground masses now carry finer structure, where a small deviation can betray the gravity of a distant world. Roman uses this delicate signal to study planetary systems in colder outer zones, to recover low-mass planets beyond the easiest reach of many other methods, and to search for planets without stars. Through microlensing, the observatory treats the inner galaxy as a vast gravitational screen on which unseen worlds briefly write their presence in light. What emerges is a gentler, broader planetary census, one built not from nearby brightness, but from transient alignments that expose the otherwise hidden abundance of worlds across the Milky Way. After the hidden planets revealed by brief gravitational alignments in the crowded inner galaxy, the view narrows again toward a different planetary region, one much closer to the light of individual stars. Here the difficulty is no longer rarity of alignment, it is brightness. A star overwhelms the faint reflected or emitted light of worlds orbiting nearby. Even when a planet is large, even when it lies far beyond the inner glare of its system, the star can outshine it by a tremendous factor. In this region, Roman turns to planets seen beside starlight, using its coronagraph to suppress part of the star's glare so that faint nearby objects and dusty structures can begin to stand out. A coronagraph is an instrument designed to block or greatly reduce the light of a bright central source. The idea is simple in purpose but demanding in practice. If the starlight can be controlled well enough, the dim surroundings become easier to detect. For Roman, this means trying to separate the light of a star from the far fainter light of giant planets and circumstellar disks around it. A circumstellar disk is a broad structure of dust and small material orbiting a star. In young systems, such disks may be linked to planet formation. In older systems, they may persist as belts of debris produced by collisions among smaller bodies. In either case, the faint material near a star carries important evidence about how planetary systems take shape and how they evolve. This is a different kind of exoplanet science from microlensing. Microlensing reveals planets through gravity during a temporary alignment, often at great distances and without the planet ever being seen as a separate point of light. Coronagraph observations aim to isolate the planet's own light, usually reflected starlight and in some cases thermal emission depending on wavelength, age, and planetary properties. The method therefore favours a different population. Roman's coronagraph is expected to be most effective for some nearby giant exoplanets that are relatively well separated from their stars in apparent angle on the sky. These are not necessarily the most common planets in the galaxy, nor the smallest. They are the planets whose light can be disentangled from stellar glare well enough for direct study. The value of seeing a planet directly is not only visual. A directly detected planet can be measured in ways that complement indirect methods. Its brightness at different wavelengths can provide clues about its atmosphere, clouds, temperature, and composition. If a spectrum is obtained, meaning light separated by wavelength, broad molecular signatures may become detectable in favorable cases. Roman's coronagraph is primarily a technology demonstration as well as a scientific instrument, and observations indicate that it can help open the way toward more ambitious future missions aimed at direct imaging of smaller and fainter worlds. Yet even within its own mission, it can study known giant planets and compare how they differ in brightness and atmospheric character. The planets best suited to this technique are often older and colder than the large hot planets found close to stars by transit surveys. A planet far from its star receives less stellar heating, and over time its own internal heat also decreases. Such a world may be dim and difficult to detect, but it occupies a regime that is scientifically important. The outer regions of planetary systems preserve information about long-term arrangement, migration history, and the role of giant planets in shaping smaller bodies. Roman's coronagraph contributes to this area by studying some of these outer giant worlds directly, not merely as influences on their stars, but as faint companions with measurable light of their own. Dusty disks are equally important in this region. Around some stars, dust forms rings, gaps, asymmetries, or broad extended clouds. These structures are not random decoration. They can be shaped by unseen planets, by collisions among planetesimals, or by the distribution of material left over from earlier stages of system formation. A planetesimal is a small body that forms in a disk and can serve as one of the building blocks of planets. When such bodies collide, they can replenish dust over long times. Roman's coronagraph can image some of these dusty environments, allowing astronomers to compare the architecture of disks with the presence and placement of planets. In this way, the region around a star becomes not just a point of light with companions, but a system whose material structure can be studied. There is a calm contrast between this method and the previous one. In microlensing, the planet is found through a brief disturbance in the light from an unrelated background star. The event does not repeat on command, and the system is often too distant for later detailed direct follow-up. In coronagraphy, the target star is chosen in advance, and the aim is to observe the system itself by controlling the central glare. The challenge moves from temporal chance to optical suppression. Roman uses careful starlight control to reveal what sits close to the star in angular terms, where ordinary imaging would leave the scene washed in brightness. The hidden planet or disk does not announce itself through a sudden transient event. It emerges slowly as the glare is reduced and the nearby field becomes visible. This work carries both scientific promise and acknowledged limits. Roman's coronagraph is not expected to image Earth-like planets around Sun-like stars in the way a future dedicated mission might seek to do. Its contrast and angular reach are better suited to brighter and generally larger targets, especially giant planets and dusty disks around nearby stars. It remains uncertain exactly how many planets or disks will prove accessible in practice, because results depend on the true properties of target systems and on the achieved on-orbit performance of the instrument. Yet observations and mission planning strongly indicate that Roman can carry out valuable direct studies of exoplanetary systems, while also testing the technologies needed for still more challenging future observatories. In this 11th region, the universe narrows from hidden planetary mass inferred through gravity to faint planetary light seen beside the glare of a star. Roman's coronagraph works at the border where a bright host threatens to erase everything nearby from view. By reducing that glare, it opens a path toward direct observation of some giant planets and dusty disks around nearby stars. The result is a quieter but more intimate picture of planetary systems, where outer worlds and surrounding material can be studied as luminous members of real stellar environments. Here the hidden is not revealed by chance alignment or by broad statistics alone, but by the careful suppression of starlight that allows faint companions and delicate dust structures to appear from the brightness beside which they orbit. After the planets and dust seen near individual stars, the path turns away from the targets themselves and toward the place from which Roman observes. The observatory does not circle Earth in a low orbit where the planet repeatedly fills part of the sky and day changes quickly to night. Instead, Roman is designed to work near the second Sun-Earth Lagrange point, often called L2. This is a region of space located roughly 1.5 million kilometers from Earth in the direction away from the Sun. In this region, the gravitational pull of the Sun and Earth, together with the motion of an object moving around the Sun, allow a spacecraft to remain in a useful relationship with both bodies. In this 12th region, Roman's story becomes one of quiet orbital setting, where stable geometry and thermal calm support sensitive observation. A Lagrange point is not a solid place or a fixed platform in space. It is a location defined by gravitational balance in a moving system. In the case of Sun and Earth, 5 such points exist. The second lies beyond Earth on the line away from the Sun. A spacecraft near this region still orbits the Sun, but in a way that keeps it roughly aligned with Earth as both move together around the Sun. Roman is not expected to sit motionless at a perfect mathematical point. Instead, like other observatories sent there, it follows a controlled orbit around the L2 region. This kind of path is often called a halo orbit or a related large looping orbit. The motion is gentle and deliberate, preserving the broad advantages of the location. The first advantage is viewing geometry. From near L2, the Sun, Earth, and Moon remain in roughly the same general part of the sky, rather than moving across widely different directions around the observatory. This makes it easier to shield the telescope from their heat and glare. A spacecraft designed for sensitive infrared measurements benefits when bright, warm bodies do not repeatedly sweep across many observing angles. Roman can keep its sun shield and thermal control systems oriented in a consistent way, while large portions of the sky remain accessible over time. The observatory is not free to point anywhere at any moment, but its allowed viewing zones are broad and orderly, making long survey planning more efficient. Thermal stability is especially important. Every warm object emits infrared radiation. A space telescope that studies faint astronomical infrared light must reduce interference from its own temperature as much as possible. Roman is not a cryogenic observatory in the same sense as some far infrared missions, but it still benefits greatly from a stable and relatively cool environment. Near L2, the spacecraft avoids the repeated heating and cooling cycles that come from passing in and out of Earth's shadow in low orbit. It also avoids the strong variable heat input that Earth would provide if the planet filled a large changing portion of the sky. A steadier thermal environment means the telescope structure and instruments can remain more stable, and that helps preserve image quality and calibration. This quiet environment also benefits the mechanical behavior of the observatory. Precision astronomy depends on control of tiny changes. Mirrors expand and contract slightly with temperature. structures flex by minute amounts. Detectors respond differently under different conditions. When the environment changes rapidly, these effects can become harder to model and correct. Roman's location near L2 helps reduce such rapid swings. The result is not perfect stillness, since all real spacecraft experience some variation, but it is a far calmer setting than a close Earth orbit would provide for this kind of mission. That calm supports the long repeated measurements on which Roman science depends. There is also value in continuous communication geometry and observing efficiency. A low Earth orbit telescope spends substantial time passing behind Earth from the point of view of ground stations and can face interruptions related to orbital motion around the planet. Roman's distant solar orbit geometry is different. Communication still requires planning and scheduled contacts, but the observatory is not repeatedly occulted by Earth in the same way. More importantly for science, it can maintain long observing sequences without frequent interruptions from Earth blocking the view or scattering stray light into the telescope. For wide surveys and repeated time domain programs, this continuity matters greatly. The L2 region has already proven its value for major space observatories. It offers a balance of thermal calm, broad sky access, and manageable station keeping, which means small propulsion adjustments that keep the spacecraft on its intended path. The orbit is not naturally permanent without correction. Tiny perturbations from gravitational influences and solar radiation pressure gradually alter the trajectory. Roman therefore uses fuel and navigation control to remain in the desired operational orbit around the region. This requirement is a normal part of life near L2. It does not remove the location's advantages. It simply means that quiet observation depends on active guidance as well as initial placement. Another benefit of this location is the reduced impact of Earthshine and the brightness of the nearby planetary environment. Earth is a large warm source of both visible reflected sunlight and thermal emission. From a close orbit, that brightness can complicate sensitive observations, especially when the telescope must repeatedly turn near the limb of the planet or cope with scattered light from Earth and Moon. Near L2, Earth is far away and remains near the same general direction as the Sun. This makes shielding and stray light control far more straightforward. The observatory's optical environment becomes cleaner, calmer, and easier to characterize. For Roman, this orbital setting is not a secondary engineering convenience. It is part of the scientific method. The observatory's large surveys depend on measuring faint galaxies with consistent image quality, tracing slight distortions in galaxy shapes, monitoring subtle variations in starlight, and suppressing bright stellar glare during coronagraph observations. All of these tasks benefit from an observing platform whose heat, illumination, and pointing constraints are predictable. L2 provides that predictability better than most alternative locations for a mission of this kind. It turns deep space into a quiet working room for astronomy. In this 12th region, the story leaves behind galaxies, stars, and planets, and settles into the calm orbital environment from which Roman conducts its work. Near the second Sun-Earth Lagrange point, the observatory moves in a controlled path where Sun, Earth, and Moon remain geometrically manageable. Heat is steadier, stray light is reduced, and long uninterrupted observations become more practical. It is a distant but deliberate perch, chosen not for drama but for stability. From this quiet position beyond Earth, Roman gains the steady conditions needed to measure faint light, subtle change, and delicate optical signals across the many scientific regions it is built to explore. From the quiet orbital setting beyond Earth, the path moves inward again to the observatory itself, beginning with its outer form. Roman is not only a telescope in the narrow optical sense. It is a complete space observatory, a working spacecraft whose external body, support structure, protective coverings, and service systems all help create the calm conditions that science requires. Before any faint galaxy is recorded or any shifting starlight is measured, the observatory must exist as a stable physical object in space, built to survive launch, unfold into readiness, manage heat and power, and maintain its shape with great care. In this region, Roman appears as an outer machine of structure and protection, assembled not for spectacle but for steadiness. Seen from the outside, a space observatory is an arrangement of necessities. It has a main body that supports the telescope and instruments, surfaces and coverings that help manage temperature, structures that connect major components, and appendages that supply power or aid communication and control. Roman follows this logic. Its exterior is shaped by the demands of balance, thermal control, stiffness, and access to the sky. Nothing on the outside is casual. Every panel, blanket, support, and hinge exists, because sensitive astronomy depends on a spacecraft that holds together under changing forces while disturbing its own observations as little as possible. The first demand placed on that outer structure comes before Roman even reaches its observing orbit. Launch is violent compared with the calm of later operations. During ascent, the spacecraft must endure strong vibration, loud acoustic energy, shifting loads, and the compression and release of mechanical forces as it rides inside a launch vehicle. The outer observatory structure therefore serves as a protective frame as much as a support for scientific equipment. It must be strong enough to carry the telescope and spacecraft systems through that brief harsh passage without allowing unacceptable deformation or damage. This is one reason why the full observatory is tested so carefully on the ground after assembly. The calm precision required in space begins with surviving a short period of controlled violence on the way there. Once in space, the challenge changes from survival to constancy. Roman's external body must help the observatory remain thermally quiet and mechanically predictable. The spacecraft is exposed to sunlight, deep cold, and the slow influence of the space environment over years. Protective surface materials and thermal blankets reduce unwanted heating and cooling, limit temperature gradients across the structure, and help keep different sections within their intended operating ranges. A thermal blanket is not a blanket in the domestic sense. It is a layered protective covering, often made from reflective materials, designed to control how heat enters and leaves the spacecraft. On Roman, such coverings are part of the calm outer skin that separates delicate observation from the harsher simplicity of open space. One of the most important visible features of a modern observatory is the sun shield. Roman uses an external shielding system to keep sunlight from directly heating the telescope side of the spacecraft, and to maintain a more stable thermal arrangement. The sun is both the ultimate source of illumination for much of astronomy and a major obstacle to sensitive observation. Uncontrolled sunlight would warm the observatory unevenly, increase infrared background, and disturb the structural stability needed for fine imaging. The sunshield therefore acts as a disciplined barrier. It helps define which side of the spacecraft faces the sun, and which side remains in the colder shadowed environment better suited for observation. This is an outer architectural decision that shapes the whole life of the observatory. Power generation also belongs to this exterior region. Roman needs electrical power for its instruments, computers, communications, attitude control, heaters, and many other systems. That power comes from solar arrays, which convert sunlight into usable electrical energy. A solar array is more than an attached panel. It is part of the observatory's physical balance and operational design. Its placement, deployment, and orientation affect how the spacecraft manages sunlight, produces power, and maintains stable pointing. The outer observatory is therefore never purely passive. Even its exposed surfaces serve active roles in sustaining the internal work of the mission. The spacecraft bus forms another essential part of the outer observatory. The bus is the service section that supports the scientific payload by providing power, propulsion, communications, data handling, and control. It is the practical body that keeps the observatory alive and directed. Roman's bus is not the target of the science. Yet without it, the telescope would remain only an inert structure. The bus carries tanks, lines, electronics, and control hardware needed for station keeping near the second Sun-Earth Lagrange point and for precise orientation in the sky. From the outside, this service structure gives the observatory much of its full physical identity as a functioning spacecraft rather than a bare telescope tube. External geometry also affects pointing stability. Roman must direct its field of view with remarkable steadiness across wide surveys and repeated observations. The outer structure has to support this by resisting flexure and by distributing mass in a controlled way. Small unwanted movements can blur images, complicate shape measurements, or weaken the performance of sensitive optical systems. Thus, the external architecture is shaped by stiffness and balance as much as by simple enclosure. Structural supports, mounting points, and body panels all contribute to a larger mechanical discipline in which the observatory behaves as predictably as possible under the mild but persistent forces of spaceflight. Communication with Earth depends on outward-facing systems as well. Antennas and related hardware allow Roman to send its data home and receive commands. Though not visually dominant in the way a sunshield or solar array may be, these systems are part of the observatory's outer working form. The images, measurements, and survey records gathered in silence near L2 only become science on Earth if they can be transmitted reliably. In that sense, the external observatory is also an instrument of connection, linking distant quiet observation to human analysis far away. There is a particular significance in Roman's completed assembled state. A modern space observatory reaches its full identity only when its major structural and service elements are integrated into one working form. At that point, the mission is no longer a collection of separated hardware. It becomes a single physical observatory prepared for system-level testing, where the outer body and the science payload must prove that they can endure launch conditions and then operate together as intended. The assembled exterior is therefore not just a shell. It is the visible expression of integration, the moment when power, protection, support, and scientific purpose are joined into one stable space machine. In this 13th region, Roman is understood from the outside inward, beginning with the observatory as a complete spacecraft body. Its outer structure bears launch loads, its blankets and shield manage heat, its arrays gather power, its bus sustains operations, and its exterior geometry preserves steadiness in the dark beyond Earth. Nothing here is ornamental. Every visible part belongs to the work of making faint and delicate measurements possible. Before light is focused, sorted, and recorded in the deeper interior, the observatory must first exist as a quiet, balanced, protected form in space. Roman's outer body provides that form, turning the general harshness of space into a controlled environment from which precise astronomy can begin. From the observatory's outer body, the path moves inward to the system that actually gathers celestial light and forms it into measured images across a broad field. Here Roman becomes most recognizably a telescope. At the center of this region stand the primary mirror and the main scientific eye, the wide-field instrument. Together they give the observatory its unusual combination of reach, sharpness, and breadth. The mirror collects faint light that has crossed immense distances. The instrument receives that light, sorts it through carefully chosen optical paths, and turns it into images and survey data on a scale far larger than the narrow windows through which space astronomy has often worked before. In this region, Roman is defined by collection and organization, where incoming light is transformed from distant arrival into structured observation. The primary mirror is the first major optical surface in this inward path. A mirror in a reflecting telescope gathers light over a wide area and directs it toward the rest of the optical system. Roman's primary mirror measures 2.4 meters across, placing it in the class of large space telescope mirrors used for high-resolution astronomy. The importance of mirror size begins with area. A larger mirror captures more light, and more collected light means fainter objects can be studied, or brighter objects can be measured more quickly and precisely. This matters across nearly all of Roman science, from distant galaxies in broad cosmological surveys to dense stellar fields in the Milky Way. Faint light becomes usable only when enough of it is gathered, yet the primary mirror does more than increase brightness. It also supports angular resolution, meaning the ability to distinguish fine detail on the sky. Resolution depends on wavelength and aperture, and a large mirror operating above Earth's atmosphere can produce very sharp images. Roman therefore combines the clarity associated with the substantial space telescope aperture with a field of view much wider than that of earlier observatories built for narrow, deep inspection. This is one of its central strengths. It does not simply magnify a tiny patch. It applies high-quality imaging to large areas, allowing broad surveys to retain fine detail instead of dissolving into coarse generality. The mirror itself must be held in an exact relationship with the rest of the optical system. A space telescope mirror is not only a polished surface, it is part of a precise geometry. Light arrives from distant sources in nearly parallel rays, reflects from the primary mirror, and is directed towards secondary optics and onward into the instrument. The quality of the resulting image depends on shape, alignment, thermal stability, and the control of stray light. Roman's optical design is therefore an exercise in disciplined order. The mirror must keep its intended figure, meaning its exact designed shape, to a very high standard. Even very small departures can weaken image sharpness or introduce systematic errors into surveys that depend on fine measurement of galaxy shapes and stellar brightness. After the primary mirror gathers the light, the wide-field instrument takes over as the observatory's main survey camera. This instrument is the central scientific workhorse for most of Roman's planned observations. Its purpose is not only to record pictures, but to provide the immense and uniform survey capability on which Roman's wider scientific goals depend. The term wide field is crucial. It means the instrument sees a much larger patch of sky in a single pointing than earlier space observatories with similar image sharpness. This is what allows Roman to move efficiently across the sky, building large coherent maps rather than only exquisite narrow portraits. The gain in survey power is profound. A field of view is the size of the sky area visible in one observation, when a telescope with sharp space-based imaging also has a large field. the amount of high-quality sky coverage it can accumulate increases greatly. Roman's wide-field instrument is designed so that it can survey areas hundreds of times larger than the narrow field observed at one time by Hubble, while still delivering comparably fine image quality. This does not make narrow-field astronomy obsolete. It changes the scale on which space-based survey science can operate. Roman can treat large portions of the sky as a continuous measured domain, rather than as a mosaic assembled only slowly from tiny windows. This broad eye is especially important for Roman's dark energy and weak lensing programs. In those studies, the telescope must record the shapes and positions of vast numbers of distant galaxies with consistency across large areas. It is also essential for time domain surveys, where the same fields are revisited and compared, and for Milky Way work in crowded regions where many stars must be measured across broad fields. The wide-field instrument supports all of this because it does not specialize in one narrow type of target alone. It is built to be a general survey engine, capable of combining sensitivity, area, and image quality in a single observing system. The instrument also operates across visible and near-infrared wavelengths, which gives Roman much of its scientific reach. Infrared capability allows the observatory to study light stretched by cosmic expansion from remote galaxies and supernovae. It also helps Roman see through dust in the Milky Way, opening views into crowded and obscured stellar regions. The main camera therefore works across multiple scientific environments without changing its basic role. Whether the observatory is surveying distant cosmic structure or mapping dense bulge fields, the instrument remains the main receiver that turns gathered light into a broad, measured record. Within the wide-field instrument, light can be observed in more than one mode. In imaging mode, the goal is to record sharp pictures across the wide field, preserving brightness, shape, and position information. In spectroscopic survey modes, optical elements can disperse the light so that it reveals wavelength-dependent features useful for estimating redshift and characterizing sources statistically across broad samples. Roman's instrument is therefore not simply a camera in the ordinary sense. It is a versatile survey system that can alternate between seeing the sky as images and reading parts of it as structured light divided by wavelength. This dual role deepens the value of each observed field, turning the same broad survey region into both a visual and a physical record. The partnership between mirror and instrument defines Roman's character at this level. The mirror alone could gather light, but without a wide and capable receiving system, the observatory would lose much of its mission purpose. The instrument alone could not create faint, sharp data without the large collecting aperture and stable optics that feed it. Together they form the main astronomical eye of the mission. One provides the light-gathering entrance to the universe. The other gives that gathered light ordered form so that faint galaxies, distant explosions, crowded stars, and wide survey fields can all be measured within a common system. In this 14th region, Roman is no longer understood mainly as a spacecraft body in space, but as an optical observatory centered on its primary mirror and main camera. The 2.4-meter mirror gathers the faint arrivals of distant light. The wide-field instrument receives that light and turns it into broad, sharp, and repeatable surveys across visible and near-infrared wavelengths. Breadth and clarity meet here in a single working eye. Through this union of collecting surface and wide-field measurement, Roman gains the ability to observe the sky not as scattered fragments, but as large, coherent regions of the universe recorded with the precision required for both cosmic and galactic science. From the main mirror and wide survey camera the path moves inward one last time to the deepest working core of the observatory, where light is no longer simply gathered or guided, but measured. At this level, Roman becomes a machine of extreme precision. The incoming light has already crossed the universe, entered the telescope, reflected through the optical system, and been directed toward the instruments. Now it reaches the surfaces and control elements that turn faint celestial signals into usable evidence. In this final inner region, the most important features are the detector arrays of the wide-field instrument and the delicate optical control systems of the coronagraph, where masks, mirrors, and sensors work together to make hidden light readable. A detector is the surface on which light is recorded as an electronic signal. In Roman's wide-field instrument, the detectors are advanced near-infrared sensor arrays designed to measure faint astronomical light with high sensitivity and stability. They do not behave like film in an older camera. They convert incoming photons into charges that can be read out, digitized, calibrated, and assembled into scientific data. At this deepest level, astronomy becomes the controlled counting of light. Every galaxy shape, every faint supernova, every crowded bulge field, and every subtle microlensing change depends on these arrays performing with accuracy over long periods. The detector plane is one of the reasons Roman can survey such a large field so efficiently. A wide field of view requires not only wide optics, but also a large mosaic of sensing elements to receive the image. Roman's main instrument uses many individual detectors arranged together to create a broad, active focal surface. The focal plane is the place where the telescope forms the image and where the detectors sit to capture it. At this point, the sky is no longer an abstract region outside the observatory. It has been brought inward and laid down as patterned light across the sensing surface. The structure of the focal plane therefore determines how much of the sky can be recorded at once, and with what fidelity. Each detector must do several things well at the same time. It must respond efficiently to faint light. It must preserve linearity, which means that stronger incoming signals produce proportionally stronger measured output within the intended operating range. It must keep electronic noise low enough that weak astronomical signals are not drowned. It must remain stable enough that repeated observations from different times can be compared. These requirements are demanding because Roman science often depends on small differences. A weak lensing measurement may rest on tiny shifts in a galaxy's apparent shape. A microlensing survey may depend on minute changes in brightness in a dense field. A time domain survey may compare repeated observations separated by days or weeks and ask whether a source truly changed or whether the instrument did. The detectors sit at the heart of that judgment. Calibration is therefore inseparable from measurement. A detector does not simply receive light and produce perfect truth by itself. It has response patterns, small imperfections, hot pixels, variations across its surface, and behaviors that depend on temperature, readout mode, and time. Astronomers characterize these effects carefully so they can remove or reduce them during data processing. Roman's observatory design, its thermal stability, and its ground testing all help support this work. But the detector arrays remain the place where raw signal first meets instrumental reality. In this sense, the innermost core of the mission is also the place where uncertainty is managed most intimately. The universe sends light, the detectors receive it. Between those two lies the exact discipline of modern observational astronomy. The chronograph moves even deeper into the problem of control. While the wide-field instrument records broad survey light across a large focal surface, The coronagraph deals with one of the most difficult optical tasks in astronomy: the suppression of overwhelming starlight so that faint nearby material can become visible. To do this, Roman's coronagraph uses specially designed masks and mirrors that work together at a level of precision far beyond ordinary imaging. A mask in this context is not a broad external covering. It is an internal optical element that blocks or reshapes part of the light within the instrument in order to reduce the bright central glare of a star. Blocking starlight is not as simple as placing a dark spot in the beam. Light behaves as a wave, so when it passes edges and openings it creates diffraction, which is the spreading and interference of waves that can produce unwanted patterns. Even a perfectly blocked central image can leave bright residual structures around it if diffraction is not carefully controlled. The coronagraph therefore uses an arrangement of masks and stops designed to shape the light path and suppress this diffracted glare. Roman's coronagraph also includes deformable mirrors, which are mirrors with surfaces that can be adjusted by tiny controlled amounts. These adjustments allow the optical wavefront to be corrected with exquisite precision. A wavefront is the shape of the advancing light field as it moves through the instrument. If the wavefront is imperfect, even by extremely small amounts, starlight leaks into the region where a faint planet or disk is being sought. Deformable mirrors can compensate for such imperfections by changing shape in minute ways. Roman's coronagraph uses this active control to create a darker region in the image where faint companions may be seen. This is among the most exacting forms of optical engineering flown on a space observatory. It turns the instrument into more than a passive receiver. It becomes an active sculptor of light, shaping and cancelling unwanted brightness so that a dim target can emerge beside a far brighter star. At this inner level, measurement becomes a battle against false light and false signal. Detector noise, residual wavefront error, diffraction, and tiny mechanical or thermal changes can all interfere with the truth the observatory seeks. Roman's design meets this by layering precision on precision. The wide-field detectors are calibrated and stabilized so the survey sky can be measured faithfully. The coronagraph's masks and deformable mirrors refine the incoming starlight so that contrast, meaning the difference in brightness between a star and a faint nearby object, can be pushed towards scientifically useful levels. Neither system creates new light. Each works to preserve or reveal the light already there by reducing the ways measurement can be deceived. This innermost region is where Roman most fully becomes an instrument of hidden things. At the outer cosmic scale, hidden influences are inferred from the arrangement of galaxies. In the inner galaxy, hidden planets are revealed through microlensing. Near bright stars, hidden worlds and dust are uncovered by glare suppression. Here, at the core of the hardware, those scientific hopes reduce to surfaces, pixels, wavefronts, and minute controlled motions. The grandeur of cosmology and the intimacy of planetary science both arrive at the same place. The exact conversion of light into trustworthy evidence. The observatory is now traced from its widest scientific horizon to its deepest mechanical and optical center. It begins with the immense structure of the observable universe, where galaxies mark the shape of matter across deep time. It moves through cosmic expansion, weak lensing, clusters, galaxy populations, changing deep fields, nearby galactic outskirts, the dusty Milky Way, the crowded bulge, hidden planets, direct planetary light, the calm orbit beyond Earth, the assembled spacecraft body, and the mirror with its wide survey eye. At last it comes to the hidden interior where detectors receive the image and controlled mirrors and masks discipline the glare. Roman's promise rests on this whole chain holding together, from distant source to final signal, with enough steadiness that what the universe has concealed can be measured rather than imagined. The night of the observatory is quiet. It moves far beyond Earth in a slow and controlled path, holding its shade against the sun and opening its eye toward the dark. The light that reaches it has travelled across distances too large for ordinary thought. Some of it leaves remote galaxies when the universe is far younger. Some of it passes through clusters, filaments, and voids. Some of it comes from stars in the crowded heart of the Milky Way. Some of it glances from the clouds of distant giant planets. All of it arrives as a thin and patient message. Roman does not hurry that message. It gathers, steadies, separates, and records it. In the wide sky, it traces the large hidden pattern of the cosmos. In the changing sky, it watches brief brightenings and fading signals. In the dusty lanes of the home galaxy, it looks through obscuring veils, near bright stars. It works to quiet the overwhelming glare so that faint companions may appear. At every scale, the observatory depends on calm structure, measured light, and the slow discipline of repeated seeing. The universe does not yield its hidden parts all at once. It gives them in distortions, in timings, in faint sources, in subtle structure, in light shifted toward the infrared, in brightness barely above the threshold of noise. Roman is built for that kind of truth. It is not an instrument of sudden certainty, but of careful unveiling, piece by piece, survey by survey, field by field. It gathers what has long remained outside ordinary sight and turns it into a quieter form of knowledge. Beyond Earth, in the cold and ordered dark, the observatory continues its work. It watches without drama, it measures without haste, and in that patient, motionless seeming labour, the hidden universe becomes a little less hidden, and the deep night becomes a little more known.